Yeah, number 37.
Is this the exam from last year?
Yes.
Excellent. This is great.
If two gases have the same RMS speed, then they must have the same average kinetic energy. That's false, because the average kinetic energy depends on two things. It depends on the speed, but it also depends on the mass. And so you could have something moving at 1,000 miles an hour, like a oxygen molecule might be moving at 1,000 miles an hour and hit you, but since it doesn't weigh much, it's not going to cause much damage. But if you had like say a bullet moving at 1,000 miles an hour, which is much more massive, then that could cause a lot of damage. And so average kinetic energy depends on both the mass and the speed, not just the speed. I think that was it for the errors in the key, unless did anybody notice any others?
Any other mistakes on the exam you haven't taken?
No, on the practice exam. No. All right, just we'll take care of any questions first. Were there any questions? Yes. Dalton's law of partial pressures. The two most common types of questions is when you collect a gas over water, we call it wet. So you might collect wet oxygen. And so if we know what the pressure of the wet oxygen is, we'd like to calculate the pressure of dry oxygen by using Dalton's law. And so that type of question we'll have. In fact, I probably gave one here. Yep, this one here, number 36. The gas is saturated with water vapor. That means the hydrogen's wet. And so out of this 758 millimeters total pressure, 23.8 of that is water vapor. The rest is hydrogen. So we have to subtract the two in order to get the hydrogen pressure. So that's the typical Dalton's law type problem. The other one is when we're doing thermodynamics, for bomb calorimetry, the pressure is going to be additive. That's more qualitative. We don't actually do a calculation. We just visualize what would happen if more gas is added to a container. More gas is added to a container, the pressure is going to go up. If gas is removed from a container, the pressure is going to go down, kind of thing. Okay, other questions? No questions? All right, something I went over on the supplemental lecture, but it's confusing, and that's the relationship between delta U and delta H. So I can review that, or I can talk about other stuff. Okay, let's talk about that then. Delta U is what we call a state function. Actually, let me back up one step here. A state function only depends on the final state and the initial state. But these values here are called the absolute internal energies. And the absolute internal energies are equal to the kinetic energy plus the potential energy. Internal energy is what we call the total energy. And so the total energy depends on the kinetic energy plus the potential energy. The kinetic energy, this is not difficult. Okay, this is easy. Actually, it's easy to determine. One way you could determine the kinetic energy is measure the temperature. You know, temperature is a measure of the average kinetic energy. Now, the average kinetic energy changes. You know, that 1/2 mu RMS squared is only for an ideal gas. An ideal gas would be like a monatomic particle, you know. If you had a diatomic, then it becomes more complicated, because in a diatomic, you're going to have vibrations and you're going to have rotations that you have to add in there. And so you'd have three terms. 1/2 mu RMS squared over 3 dimensions. That would be the translational. Then you'd have the vibrational, which is like Hooke's law, if you've ever heard of Hooke's law in physics. Then you'd have rotational. And so you'd have to add those terms. And then as the molecule complexity grows, so does the equation. So, but nonetheless, even if it's a complicated molecule, we can still determine the kinetic energy. What about the potential energy? Is that something that's easy to determine? No. This is difficult. Why is it difficult? Well, it's like the, think about this. If you think about the redox chart, what is the strongest oxidizer on the chart? Fluorine, F2. Do you know what the weakest oxidizer on the chart is? Lithium ion. And so if you ever look at the numbers on the redox chart, take a look at the numbers that they have here. Did I put the numbers? Yeah, I put the numbers on here. So if lithium ion were the weakest, we should assign this absolute 0. This is the absolute 0 of oxidizing agents because it's the weakest. It's the bottom, right? You can't get any weaker. And therefore, we should call it 0. It's like the elevation. You know, what's the lowest elevation we can go? The lowest elevation we can go is over at the Badwater in Death Valley. It's like minus 200 feet below sea level, or was it minus 21 feet? I forgot. I think it's minus 200 feet below sea level. Is that really the lowest you can go, though? Because somebody could go lower. They could just dig a hole. Is this really the weakest oxidizer that exists in the universe? No. So it's your job to find the weakest oxidizer that exists in the universe. And then we're going to call that 0, because that's the bottom. You can't go any lower than that. It's like temperature. You can't go any lower than 0 Kelvin. So once we know where 0 Kelvin is, then we'll assign it 0. That's what we call absolute. But you might think you've discovered it. You know, I've discovered the weakest oxidizer in the universe. And then somebody else comes and says, no, you didn't. I have. You know, I now have the weakest oxidizer on Earth. And you can make an even weaker oxidizer than the previous one. So where does it stop? And so people just gave up. They gave up and they came up with an arbitrary 0. You know what the arbitrary 0 is? Hydrogen. We're going to call, is hydrogen the weakest in the universe? Is that why it's 0? No. They just said, okay, we're just going to call this sea level. And we'll have things below sea level and things above sea level. But we're just going to call hydrogen 0. It's totally arbitrary because H plus is a really decent oxidizer. H plus, you can eat away things like magnesium, aluminum, iron. All those metals are eaten away by H plus. It's a pretty, what we call a pretty moderate oxidizer. Why is it assigned 0? Because nobody wants to find the bottom. It's a futile thing to do. And so, in a way, finding the bottom of potential energy is a little bit futile too, because, you know, what's the potential energy of a nucleus? Well, the potential energy, you got the protons and neutrons, break those apart. But then you get the protons. Can you break the protons apart? Yeah, you can break them up into quarks. And then, are there things smaller than quarks? Well, I think current particle physics there isn't, right? The quarks are it. But really, is that the absolute bottom? Well, it could be, but you know, even if we call that the bottom there, and we do the calculations are not very accurate, you know, because when you compare them to experimental delta U values, they're off significantly. And so this is a difficult thing to answer. We could come up with an arbitrary zero, but you know, when we're doing absolute internal energy, then we need absolute potential energy. We don't need an arbitrary. You know, this is like having Kelvin and throwing Celsius in there. It just doesn't make sense to mix and match. So we don't do this, U final minus U initial, but we take advantage of the first law of thermodynamics. And so the first law of thermodynamics says that any energy lost or gained by the system will be exchanged with the surroundings. And when we exchange energy with the surroundings, it's going to be in the form of heat and in the form of work. So heat and work are exchanged. Heat and work is equal to the energy exchange with the surroundings. These are easy. Well, relatively easy. I mean, heat is calorimetry. Calorimetry is a pain. It can be tedious, but it's not too difficult. Now, work we can measure. I mean, there are different kinds of work. There are many different kinds of work. Like gravitational work or whatever is not too difficult because it's just lifting. You know, how high are you going to lift this mass? And so that's easy to calculate. We have electrical work, etc. And so this is fairly easy to determine. These are difficult. It's difficult because of the potential energy term, not because of the kinetic energy term. Now, we run into a problem, and the problem is delta U is a state function. Q and W, even though they're easy to determine, these are not state functions. If it's not a state function, we call it a path-dependent function. So path-dependent. Path-dependent would be something like if you were to go from the bottom of the valley to the top of the mountain, that's a change in altitude. Delta altitude is a state function. Let's say it's a 3,000-foot climb to go from the valley to the top of the mountain. The path-dependent function would be how you get there. So you could either hike up from the valley to the top of the mountain, or you could take a helicopter or a chairlift or something like that. And so those would be path-dependent. And so the situation here is when we have a path-dependent function, we don't always get the same amounts of heat and work. Not always the same amount. Of Q and W. And so we can think of this like in terms of a battery. The energy content, the chemical potential energy stored in a battery is fixed. So if I have two AA batteries, they have the same energy content. You know. It depends on how precisely they're made, but they should have exactly the same. And so the delta U for this AA battery and the delta U for this AA are the same. That is a charged and a discharged. And so U initial, U final. U initial is fully charged, U final could be fully discharged. And the energy constant is the same. So the delta U between the two batteries is the same. But does that mean that, battery A, or I shouldn't call it A, I'll call it battery 1 versus battery 2, am I going to get the same amount of heat and work from both batteries? Do I always get the same amount of heat and work from AA batteries? No, it depends on what you connect the AA batteries to. So heat and work are path-dependent functions. So I could connect battery 1 to a little portable heater. A portable heater might be like a wire, and this wire has what we call resistance, electrical resistance. So as electrons try to flow through the wire, there's vibrations in the metal lattice, and those vibrations cause the electrons to have, let's say, not an easy path through the wire, but it's going to be a path full of collisions with these vibrating atoms. And that's going to result in friction, you could say, and then what's going to come off this is heat. And so there's going to be work. There's going to be work in pulling the electrons through the battery, and there's going to be some friction. So here we're converting it mainly into heat, and so the battery is producing a lot of heat. And so this would be on a cold day. On a hot day, you don't want to produce heat. Maybe on a hot day, what we want to do instead is we want to power a electric fan. And so there's going to be an electric motor here, and then there'll be a fan blade here. And so in this case, we'd like to convert it all into work. And so battery 2, we want to convert it into work. However, it's not thermodynamically possible because, there's going to be heat that's going to be coming off the motor here. And then there's going to be friction with the air, so there might be some heat. Hopefully there's more cool air coming from this, but there's going to be some heat. But primarily it's going to be work, the work of spinning this around. And so here we have a case where delta U is primarily converted into heat, and over here we have the same exact delta U, but it's converted into a little bit of heat and hopefully a lot of work, or some combination. If it were possible to make this 100% efficient, then we can convert all this chemical potential energy into work. But it's difficult to. Now, the chemical potential energy is via redox reaction. So in this redox reaction, we have typically in a battery like this, we'd have zinc as the reducing agent, and we'd have an oxidizing agent. The oxidizing agent is like MnO2, manganese 4, it's a solid. And then what we end up doing is we end up making Zn2 plus and Mn2 plus other stuff. And when we do this reaction, we start off, let's say, at 25 degrees C initial, and we end up at 25 degrees C initial. So was there any change in kinetic energy? If we start at 25 and end at 25 degrees C, did the kinetic energy change? No. So delta U is equal to the change in kinetic energy plus the change in potential energy. And since we are starting and ending at the same temperature, the change in kinetic energy is 0. Therefore, this is just a change in potential energy. And so the change in potential energy comes from this. Zinc metal is a stronger reducer than manganese 2 plus, and MnO2 is a stronger oxidizer than Zn2 plus. So we're going from stronger reducer, stronger oxidizer, to weaker oxidizer, weaker reducer here. And so that's our driving force. And so that's chemical potential energy. And this chemical potential energy is going to be released into the surroundings as heat and work. But heat and work are not state functions. So this change in chemical potential energy is going to be released into the surroundings as heat and work. And these are path-dependent functions. And so it depends on the path we take. Should we take path 1 over here and generate lots of heat? Or should we take path 2 and try to generate lots of work? So what we want to do is this. We want to have a consistent amount of heat produced. Because heat is something that we're going to measure. If we want to measure what delta U is, how do we determine what delta U is? Are we going to determine delta PE? The change in potential energy, that is, get the initial potential energy and the final potential energy and subtract those? No, it's too hard. And so if we want to figure out what delta U is, we have to measure the heat and the work, and then it's easy, right? But measuring the amount of work sometimes isn't so easy. So what we want to do is we want to have a consistent amount of heat. And so heat varies. Heat varies depending on path. There are two ways to make heat a state function. One, we do this under constant volume. Bomb conditions. And so if we use a constant volume bomb, can any work be done inside the bomb? No. There's no work that's going to be done inside the bomb. That is, we don't have a fan in there, we don't have anything in there, it's just empty, this bomb. No work is done in there. So when we're looking at delta U, delta U is equal to Q plus W. If we do this in a bomb, then the volume can't change, so we call it QV. And if it's in a bomb, then no work can be done, and so that's 0. So what we can do is we can get delta U. Delta U is just equal to QV. So if we want to figure out the change in total energy, we just do the reaction in the bomb. We do it in the bomb calorimeter. If we do it in the bomb calorimeter, then the total internal energy change inside the bomb is going to be exchanged with the surroundings as heat. And so we just measure how much the surroundings warm up or how much the surroundings cool down, and then we can figure out the delta U for the bomb. It's a little bit more than this. I mean, this is the equation here, but typically delta U is in units of kilojoules per mole. So we'll put QV over the amount in moles. Typically this is in moles. It could be in grams. And that way we get the typical units of kilojoules per mole. QV is either in joules or kilojoules. And so we might have to do this an extra step. So you have to know this. Bomb calorimetry measures delta U. If we want to know what delta U is, just throw it in the bomb, do the calorimetry experiment, and then we get it. So it depends on how many grams of reaction you have in here. So if you're going to combust something, throw 5 grams in there, and then measure how much heat, and then you get the joules or kilojoules per gram, and then we can convert it to joules or kilojoules per mole. This is the total internal energy chain. But the problem is this. Do you work with bombs inside the laboratory? No. We don't work with bombs. And it would be fine if we get the same amount of heat under constant pressure conditions, but we don't always get the same amount of heat under constant pressure conditions. And so, number 2, under constant pressure conditions, this would be like a coffee cup or whatever, just normal conditions.
Coffee cup in a vacuum?
No, no vacuum, just coffee cup or normal conditions. The way we do this is we have two restrictions. One, which we already talked about, constant pressure. And the other is restrict the work to minus P delta V work only. And so PV work, restrict PV work only. And so here we have delta U is equal to Q plus W. And what we're going to do is we're going to restrict it to constant pressure. So rather than calling it QV, we're going to call it QP. And the work is going to be a minus P delta V. This is going to be for the system.
Should you scroll up just a little bit? Oh, sorry, down.
Okay.
Does that not say 6?
Here?
No. Other way. Sorry. Thanks.
Okay.
I'm sorry, what's under you?
System, SYS, yeah. And therefore, QP of the system is equal to delta U of the system minus the work of the system. The work of the system is delta U of the system minus a minus P delta V of the system. So what this is saying is the amount of heat under constant pressure is going to equal the total energy change minus the work. The work is minus P delta V. Okay, what we've done here is delta U of the system, this is a state function. The state function doesn't depend on path. We're always going to get the same amount. It's like the AA battery. It doesn't matter how you use it, it's going to give you the same amount of energy. Pressure is also a state function, because if we think about a change in pressure, let's say the pressure increased from 1 atmosphere to 2 atmospheres, then what was the change in pressure? So if we went from 1 atmosphere to 2 atmospheres, the change in pressure was plus 1 atmosphere. But it doesn't matter how we got there. So we could have gone from 1 atmosphere to 1,000 atmospheres and back to 2 atmospheres. Delta P will be the same regardless of how we do it. And so P is called a state function. How about delta V? Delta V is also a state function. It doesn't matter. If you had a 1 liter volume change, it doesn't matter how slow, how fast, how big it got, how small it got. It just matters what the initial and the final are. So both of these are state functions. And so what that means is that if both of these are state functions, then Q is also a state function. Therefore, QP is also a state function with these restrictions. And what that means is we're always going to get the same amount of heat. Each time we do this reaction, we'll get the same amount of heat. Well, it makes sense, because if we always do the same amount of work, we're always going to get the same amount of heat, so we restrict it. And what type of work are we going to do? What we're going to do is the natural work of a chemical reaction. In order to maintain constant pressure, you have to allow for expansion and contraction of the system volume to compensate for gases being generated and gases being consumed. And so now QP is a state function, and therefore we should give it a new name. And the new name that we give it is, do you know the new name that we give it? Delta H. And so delta H is just QP. And this is called the enthalpy change. It's a restricted QP. Only one type of work. So we can't have electrical work, we can't have sound, we can't have light. It's only pressure volume work. So this is going to be very useful. And what we're going to do is we're just going to measure the heat at constant pressure. And that'll give us delta H. And so this is what we did in lab. In lab, we measured the heat at constant pressure, so we're determining delta H's. Delta H's are going to be very useful for us because they'll allow us to calculate, amounts of heat required for, or how much change we can accomplish with a given amount of energy. And so, let's see. We don't ever calculate it using absolute enthalpies. These are difficult. And so when we look at the enthalpy like this, we are just looking at changes in enthalpy, delta H. When we look at absolute enthalpy, let's say this is H initial here. H initial is going to equal the initial absolute internal energy minus a minus PV. Actually, is that? Let me just make sure. Yeah. And H final will just equal the absolute internal energy final minus the work, which is a minus PV. We can multiply the minus through and just get plus PV. So this is PV initial, this is PV final. And so what this is showing is that enthalpy is just the total energy. And so we're looking at the total internal energy change. But normally when we look at the total internal energy, we're just looking at the system. We ignore the surroundings. But do you know the surroundings can take away energy or give energy to the system? And the way that surroundings takes away or gives energy is by the work interaction. And so what we have to do is we have to add the PV state. This is an energy state here. The PV state initial and the PV state final. With the PV state, we can determine how much energy is exchanged with the surroundings if a gas expands or a gas contracts. So if the system's volume expands, the system loses energy in expanding its volume, but the surroundings, because of the first law of thermodynamics, the surroundings gains that energy. If the system's volume contracts, then what happens is the system gains energy. It gains energy from the surroundings because if the system's volume contracts, the surroundings volume must have expanded. And so we need this PV term to determine how energy is exchanged with the surroundings for volume changes. Does that make sense? And so enthalpy is just like the total energy change, factoring in volume changes, which are going to interact with the surroundings. And so since we live in a constant pressure world, we want delta H. So we should just completely ignore delta U, right? But we can't, unfortunately. We can't ignore delta U because can you do combustion calorimetry in coffee cups? No. That would be a problem. So the situation is many reactions have to be done in a bomb, So what we end up with is from bomb calorimetry, we get QV, and from QV we get delta U. But the situation is this. Are we going to get the same amount of heat if we burn, let's say, if I combust methane in a bomb, versus methane in the open laboratory, will I get the same amount of heat? Maybe, maybe not. And so we have to look at it case by case. And so what we need to do is we need to figure out what the amount of heat would be under constant pressure conditions, because this is the world we live in. And so even though we might do the combustion calorimetry in a bomb, we're going to have to correct it for constant pressure. So we have 3 scenarios that come up. 1, they're equal. 2, the delta U is bigger than delta H. 3, the delta U is smaller. Delta H is bigger. So we have those. And so the first thing is we're going to look at this qualitatively. And then we'll look at it quantitatively. So we're going to go back not to the enthalpy diagram. This is called an internal energy diagram where we plot U. We don't calculate the absolute internal energy, so I don't put any numbers to this. All we do is we determine delta U, the change in U here. So delta U we can get from bomb calorimetry, that's just QV. And so we do this in a bomb. Now, what if we did this in the open lab? And so this is constant volume. What if we did this under constant pressure? If we do this under constant pressure, 3 scenarios come up. One scenario is this. And so we have to look at volume changes first. Solid to solid, liquid to liquid, solid to liquid, liquid to solid. Does the volume change? Yeah, it could change because, different solids have different densities. Some solids are more dense, some solids are less dense. But the situation is this. Is the volume change very significant? In the thermodynamic scheme of things, these are kind of negligible. These are very small volume changes. So if we go from one solid to another, will the volume change by a liter? No. If we go from one solid to another, the volume is going to change by a tiny bit. But how much energy is that? Well, did I calculate how much energy is required to blow up a 1 liter balloon with an external pressure of 1 atmosphere? Did we do that? We didn't do that? Shoot. I guess
Is that not as complicated as it sounds?
It's not complicated at all.
But you have to factor in the rubber?
Well, I'm sorry?
You don't have to factor in the tension of the rubber?
No.
Oh.
We're not going to get that.
That sounds quite simple then.
Yeah, it is simple. These are small volume changes which lead to negligible energy changes. The reason they lead to negligible energy changes is because of the amount of work. And so let's say we go from 0 volume to 1 liter of volume. And so we're going to blow up a 1 liter balloon. And let's say the external pressure here is 1 atmosphere. And so the amount of work is equal to minus P delta V. So P is 1 atmosphere, and delta V is 1 minus 0, so it's 1 liter. And this comes out to minus 1 liter atmospheres worth of work. Did I talk about the conversion factor between liters, atmosphere, and joules? Yes? No? The conversion factor is this. It's 101.3 joules per liter atmosphere. And so this is going to be, we're going to lose 101.3 joules of energy. 101.3 joules sounds like a lot of energy, but it's actually kind of small because most of the heats involved here are thousands of kilojoules. If you had 1,000 kilojoules, then this is just 0.1 kilojoule. Is that significant?
Was 1,000 kilojoules called a joule?
1,000 kilojoules is typical for heat, and the amount of work here is 0.1 kilojoules. Is it very significant? No, that's for 1 liter. If we did 24 liters, it would be more significant. If we did 50 liters, it would be more significant, but still it's relatively small. And so, now, if we go from solid to solid, we're talking about maybe 1/10 of a milliliter or a milliliter. If we're talking about a milliliter volume change, is that even going to register on the energy? Not really. And so what we're looking for here is we're looking for something called delta N of gas. We look at the reaction and we look, are we forming gas or not? If delta N of gas is 0, let me give you an example of that. An example would be, let's say I had 2A gas goes to B gas plus C gas. So I have 2 moles of A gas going to 1 mole of B gas and 1 mole of C gas. And so initial, I have 2 moles of gas. 2 moles of gas under normal conditions is how many liters, roughly?
Oh, wait, say that again.
2 moles of gas under normal conditions is roughly how many liters? 49 liters. That's pretty precise. Or I just say 50 liters. It's about 50 liters. Then we go to 2 moles of gas in product. 2 moles of gas on product is roughly how many liters? 50 liters. So if we did this in a bomb, there's no change in volume because we start off at about 50 liters. We end up at 50 liters. So in a bomb, the volume can't change, but even if we do this under constant pressure conditions, does the volume change? No, if we did this under constant pressure, the volume doesn't change either. And if the volume doesn't change, is there any work done? No, there's no work done. So what that means is that delta U is equal to QP plus W. QP is what we call delta H. And so delta U is equal to delta H, actually, plus W. W is 0 because there's no PV work done. And therefore, delta U and delta H are the same thing. So when delta N of the gas is 0, then delta U and delta H are the same. And so whether we burn it in a bomb or we burn it in the open lab, we're going to get the same amount of heat. All right, still continuing on with constant pressure. We look at delta N of gas. Actually, delta N of gas we could see in any of these. Delta N of gas can be anything. Delta N of gas can be equal to zero, greater than 0, less than 0, it doesn't matter. In a bomb, the volume never changes. But under constant pressure conditions, let's say delta N of gas increases. Actually, is greater than 0. So delta N of gas is greater than 0. An example of this would be, let's say we go from A liquid to A gas. So if we go from A liquid to A gas, what is delta N of gas here? Delta N of gas is we're adding 1 mole of gas. 1 mole of gas, if we're adding 1 mole of gas, how many liters did this have to expand by? Roughly 24.5 or 25 liters. And so the volume expanded. If the volume expands for the system, who does the work? The system does the work. So we look at our delta U. Delta U never changes. That's a state function. But this is delta U is going to equal Q plus W. So it depends on how much work we did. So let's say delta U is 1,000 kilojoules. So let's say we get minus 1,000 kilojoules. So we expect 1,000 kilojoules of energy released by the system. But how much energy will be released by the system? Well, it depends on how much work is done. And so let's say I had 100 kilojoules of work. And so the system's going to lose about 100 kilojoules in doing the work. How many kilojoules of heat am I going to get? I'm only going to get 900 kilojoules of heat. And so my delta H is 900, whereas my delta U is 1,000. And the reason is because the system's volume expanded, and therefore some energy was used in blowing up the system volume. Therefore, there's less energy available to the surroundings. So this was supposed to output 1,000 kilojoules, but it only outputted 900 kilojoules because 100 of those kilojoules were consumed in doing the work. Does that make sense? Okay. So what we say here is this. We say that delta U is greater than delta H. Delta U is minus 1,000 kilojoules. Delta H is minus 900 kilojoules. Some people get confused with this because they think which is the lower number, which is the smaller number, and they think minus 1,000 is smaller than minus 900. You know, if you're 1,000, isn't that lower than 900? But in terms of energy, the sign just tells us the direction. Minus 100 means we're losing. And so this is the direction of change. Direction of change. Which is a bigger change? $1,000 or 900? 1,000. So that's it. All right, now the next scenario is under constant pressure. We're going to have delta N of gas be less than 0. So an example of this would be something like 3 moles of A gas goes to 2 moles of B gas. So the system loses about 25 liters here. And so we're going to have to do some work. But who does the work? Does the system do the work? If the system volume contracts, you know, if the system volume contracts, the system doesn't have to do the work. What's happening is the surroundings is collapsing it, the volume. If the surroundings is collapsing the surroundings volume has to grow, and therefore the surroundings blows up the balloon. If the surroundings blows up the balloon, then the work is done by the surroundings. And so delta U is the same. Let's say delta U is equal to minus 1,000 kilojoules. But let's say in this particular case that the surroundings had to do 100 kilojoules worth of work. That means the surroundings loses energy and the system must gain that energy. So if the surroundings loses 100 kilojoules in doing the work, the system must gain that 100 kilojoules. And so if the system gains that 100 kilojoules, then the arrow is pointed up. And therefore the amount of heat is going to be this. The amount of heat is going to be more because we have to compensate for that. And so Q in this case is going to equal minus 1,100 kilojoules, which is going to equal our delta H. And so in this final scenario, delta U is less than delta H. Over here, delta U is equal to delta H. And over here, delta U is equal to QV. So the amount of heat depends on who does the work. Who does the work depends on delta N of gas. If nobody does the work, delta N of gas is 0. If delta N of gas is greater than 0, the system does the work. If delta N of gas is less than 0, then the surroundings does the work. If the system does the work, then the system loses energy doing the work. If the surroundings does the work, then the system gains energy doing the work.
Is this a large part of the exam?
No. But it's confusing, I think. I don't know. Is it confusing or is it clear?
Well, I've heard that before.
If it's clear, the only reason I'm going through it is because it confuses a lot of people. Let's burn some methane. I'm going to burn a mole of methane. What does it form? In water. Will the water be liquid or gaseous? It should be liquid. The reason it's going to be liquid is because we're going to start the combustion at 25 degrees C, and then we're going to end the combustion at 25 degrees C. So at 25 degrees C, water is much more stable as a liquid than a gas. In fact, the preferred state of water is liquid. And what we have here is this. We have delta U. And delta U is going to equal the change in kinetic energy and the change in potential energy. Was there any change in kinetic energy here? No. So the change in kinetic energy is 0. And the change is in potential energy. But can we measure the initial potential energy and the final potential energy? No. So we have to get this using Q and V. Not V, Q and W. Sorry. If we do this in a bomb, can any work be done? No. So if we combust this, we should use a bomb calorimeter. We don't want to combust this in coffee cups. So if we use a bomb calorimeter, the work must be 0. And therefore, delta U is equal to QV. Now the situation is, I want to do this not in the bomb calorimeter. I want to figure out how much heat I get under constant pressure conditions. Will I get the same amount of heat under constant pressure conditions? Or will I get more heat, or will I get less heat? And so this would be a typical exam question. What gives off more heat? Burning methane in a bomb or burning methane in the open lab? Which one gives more heat? And the answers could be, well, they give the same amount of heat. Or the answer could be, we get more heat in the bomb. Or the answer could be, we get more heat in the open lab. Which one gives us more heat? To answer that question, all we do is this. We look for delta N of gas. And so that's all we do. We just look at delta N of gas, and that's going to tell us. What is delta N of gas here? So we have 1 mole of methane gas plus 2 moles of oxygen gas, so this is about 75 liters. Going to 1 mole of CO2 gas plus 2 moles of H2O liquid. A mole of CO2 gas is about 24.5 liters or 25 liters, and 2 moles of liquid water is about 36 milliliters, or 0.036 liters. 0.036 liters compared to 24.5 or 25 liters, is it very significant? No, so we call it negligible because we'll probably round it off anyway. Does that make sense? And therefore, we're going from 50 liters to 25 liters. We're losing about 25 liters of volume. So we go from a 50-liter balloon to a 25-liter balloon. The system volume contracted. Who does the work? The surroundings did the work. And so delta N of gas is negative. I.e., it's less than 0. If it's less than 0, the system volume contracts. Therefore, surroundings does the work. System gains energy. Delta U is fixed, but if the surroundings does the work, then that means the work is positive, and that means delta H, the heat under constant pressure, will look like that. So which one is bigger, delta U or delta H? Delta H is bigger. How can we get more energy than the total energy? Well, when we're looking at it, it's called the internal energy. It's the total energy of the system. We're ignoring the surroundings. And when we factor in the surroundings, we get more energy than the total energy. We get more energy than the total energy because the surroundings is going to give us energy by contracting the volume. Does that make sense? And so we end up getting more heat by burning it outside the bomb than inside the bomb. Well, we're always going to burn it outside the bomb because we don't work in a bomb. So we want to figure out what our delta H is, not what our delta U is. And so the next step is, well, we got to figure out what our delta H is, not our delta U.
Wait, am I a bomb?
Hmm?
Am I a bomb?
You could buy a bomb, but
No,
let's...
am I a bomb?
Huh?
Am I a bomb?
You're not a bomb. You're constant pressure. If you're a bomb, then you'd be like, what was I looking? I was like, there's this...
There's definitely been times in my life where I wasn't at constant pressure, but that makes sense.
Yeah, I was watching like this
No.
these what was it, the I don't know, this is some safari African thing, and there's an animal feeding on a hippopotamus, but the hippopotamus was ballooning out. I think it was a hippo. It was ballooning out, and they're saying, oh, this is very dangerous. There's a unsuspecting animal that's feeding on it, and it's a potential bomb, because
there's a whale that blew up.
yeah.
And killed a bunch of people.
Yeah, the whale that blew up.
That
Yeah,
was pretty crazy.
yeah. So not yet. You're not a bomb. You gotta wait until.
I gotta go to Chipotle or something.
Anyway, so now we got to figure out, well, how much extra work are we going to get? And so what we need to do is we need to get our delta U value from calorimetry. We can get our delta U value from calorimetry. In fact, I had it. Did I have it on the practice test? Let's see. I guess it would be practice test 3. Maybe I didn't. Minus 890. So let's say we do this is for 1 mole of methane gas reacting with 2 moles of oxygen gas to get 1 mole of CO2 gas plus 2 moles of H2O liquid. Oops. So delta U is equal to delta H plus W. That's QP. All right, so what I want to do first is I want to just do some conceptual stuff first. Delta H is equal to delta U minus W, or delta U minus a minus P delta V. This is W here. Pressure volume work. And so the way I think about this is what I did on the supplemental video too. This is your gross. And so let's say you started a job and they promised you, let's say, $1,000 a month. They promised you $1,000 a month, but when you got your first paycheck, it was way less than $1,000. Do you know why? Yeah, because that would be your net pay, because there's withholdings. You know, you're going to have to do state and federal income tax and disability and Social Security, and so there's a tax associated with it. And so you take your gross income. Let's say should have been $1,000. You have $100 in tax. You only net $900.
Wait, is that done automatically?
Automatic?
Yeah. Like, they take that out automatically, or do I have to go pay someone?
No, they take it out automatically. Yeah.
I'm making a lot more in tips than I thought I was.
Oh, well, and there's going to be, what, no tax on tips maybe after the next election, right? I mean, no matter who wins, if they follow through with that. So anyway, you have a tax. The tax only occurs when delta N of the gas is greater than 0. There's going to be a tax on the system. The tax on the system is having to blow up the balloon. Or there could be no tax. You know, you have those tax-free days where you go in and you don't have to spend extra money paying tax. You know, so the sticker price is the out the door price. Okay, that happens when delta N of the gas is 0. And so there's no work. And the work is the tax. Or sometimes you get more than let's say they really like the work you're doing and they gave you an extra $100 and then they decided to pay the tax. And so this we would call a bonus. You get a bonus when delta N of the gas is less than 0. The surroundings gives you a bonus. And so the bonus is from the surroundings. So now what we're going to do is we're going to calculate, are we going to have a tax or a bonus? So we go back here and let's take a look at delta N of gas. What do we see as our delta N of gas here? So what we have is we have 3 moles of gas here. Actually, I shouldn't have written moles here. There's 2 O2s. This is 3 moles of gas. And down here we have 1 mole of gas. So delta N of gas is going to be 1, the final, minus the initial, 3. It's minus 2 moles of gas. So if we have minus 2 moles of gas, is that going to be a tax, no tax, or a bonus? It's going to be a bonus. Do you see that? It's going to be a bonus from the surroundings. And so let's take a look at how much that bonus is. And so delta H is equal to delta U minus 890 kilojoules per mole of methane. Okay, minus the work. And so that's going to equal minus 890 kilojoules per mole of methane minus a minus P delta V. So the pressure we're going to just assume is 1 atmosphere. And what was our delta V? Minus 2 mole. No, actually our delta V is not that. This is why you want to know the molar volume of a gas. If we lose 2 moles of gas, what was the volume change? Minus 49 liters under normal conditions. So times a minus 49 liters. So minus times a minus is a plus. And so this is going to give us 49 liters atmosphere. So we're going to get minus 890 kilojoules per mole of methane minus, this is times, 49 liters atmospheres. And then we're going to convert this into joules per liter atmosphere. And then we're going to convert it to kilojoules. So I'm going to get the second term here. The second term is going to be 49 times 101.3 divided by 1,000, 4.96. So we're going to get minus 890 kilojoules per mole of methane combusted, minus 4.9637 kilojoules This is also going to be per mole of methane combusted. So that's going to give us minus 894.9 kilojoules, or minus 895 kilojoules per mole of methane. So the surroundings, let's call this dollars. The surroundings is expecting $890. The surroundings are going to get $895. They're going to get a little bonus because even though it sounds counterintuitive, the surroundings is doing work, and so contributing to that bonus. Does that make sense? So in terms of an internal energy diagram, delta U never changes, and so delta U is going to be the same here.
So is there just like a wizard in my freezer? Like what's happening? How does that work?
In the freezer?
Yeah, what's doing the work there?
Of cooling it?
It's taking away energy, right?
What's taking away energy is vaporizing a liquid. So in a freezer, you have delta H of vaporization of a liquid. And as this liquid vaporizes, it takes heat from the surroundings. And so what happens is the liquid gets vaporized, cooling the surroundings down. But then you're going to run out of liquid. And so the gas is pumped to a condenser. And the condenser is a pump that compresses it back down into liquid, and then it just recirculates.
Where does the heat that's taken from the stuff go?
Well, the heat that's taken from the stuff goes out either a radiator or straight from the condenser, and it gets hot. If you ever touch the back of the condenser, it's extremely hot. If you go underneath a freezer or refrigerator or into the back of it, it's very hot. So it's just taking heat from one place and transporting to another place. But those are objects. It's not a chemical reaction or anything. This is a chemical reaction here where delta H is greater than delta U. And that's because there was some work done by the surroundings. The work was, oh, actually, no. Sorry, I got this wrong. Did I get this wrong? I think I got this. I think I screwed up this sign here. Because who did the work? Oh, actually, the surroundings did the work, right? And so the surroundings did plus 5 kilojoules worth of work. This is minus 890 kilojoules. And so this is going to be minus 895 kilojoules. And again, the work of the system was equal to minus P delta V. And delta V, the volume contracted, so it's negative. Yeah, so it's positive. So the work was plus 5 kilojoules. All right, does that make sense? So this is what we have to do, because a lot of reactions, especially combustion reactions, we do in a bomb, but we have to determine the amount of heat under constant pressure conditions. All right, were there questions on other stuff? So, what you want to do is you want to do the conceptual problems in the homework. Let's see. Let me take a look at those. See if we could figure these out. Heat capacity and specific heats of reaction. So this is the kind of stuff we want. The heat evolved under constant pressure conditions. This is already under constant pressure conditions, so we don't have to change that. So we can take a look at this here. Pass it. Only one of the following quantities is equal to the heat of a chemical reaction, regardless of how the reaction is carried out. Which one and why? Only one of these. Regardless of how the reaction is carried out. QV means the reaction has to be restricted to what? Constant volume. If you do it under constant pressure, are you going to get the same amount of heat? Maybe. Maybe not. QV is not it. QP, constant pressure. Delta U minus W. This delta U minus W is what we call delta H. Delta H requires constant pressure usually, although this depends on the work term. If you have any type of work here, then it depends on the type of work. This one we don't know, because we could have PV work, we could have electrical work, we could have mechanical work, we could have gravitational work. How about delta U? Delta U doesn't. Delta U just depends on the kinetic energy and the potential energy change. Delta H of R, that depends on constant pressure, so the answer is D. Does that make sense for that? Only the internal energy. It could be C, however, we don't know what type of work they're talking about. And so that's a problem. if they always make it the same type of work, then it should be okay. That would be, if we always make this only, the restriction for delta H is we always make it only PD work, and this has to be a constant pressure. So there's too many restrictions, and they're saying no matter how it's carried out. The following reactions take in a constant pressure vessel. The following reactions take place in a constant pressure vessel. Is delta U equal to, greater than, or less than delta H? And so we just have to remember these things. But since the only significant change in volume is the change in the amounts of the gases. Decomposition of potassium permanganate to produce oxygen along with manganese for oxide and potassium permanganate. So here we're producing oxygen. Potassium permanganate's a solid, and potassium manganate's a solid. And so if we're producing oxygen gas, delta N of gas is positive. If delta N of gas is positive, then who does the work? System does the work. So that means if the system does the work, the system loses energy. If the system loses energy, then delta H should be less than delta U. Delta H, you remember delta U has no work. And so if we're going to lose energy doing work, then we're going to lose energy. Well, B, formation of nitrous oxide gas owing to the reaction between nitrogen gas and oxygen gas. So I should write it down here. So we form nitrous oxide from nitrogen and oxygen. Nitrous oxide is N2O. All these are gases. So what's delta N of gas here? Plus or minus? It's minus 1/2 mole. So delta N of gas is minus 1/2 mole. We're going from 1.5 to 1. So that means the system loses energy or system gains energy? System gains energy. If the system gains energy, then delta H should be greater than? Greater than delta U. So next. Formation of water from its elements. Elements would be hydrogen and oxygen, so delta N of gas is going to be, we're going to lose gas to form liquid. Therefore, delta N of gas will be negative. If it's negative, then system gains energy, so delta H should be greater than, etc. All right, 65. The heat of combustion of propane 2-ol at 298.15 Kelvin determined in a bomb calorimeter is minus 33.41 kilojoules per gram. For the combustion of 1 mole of propane 2-diol, determine delta U. So this is our delta U in kilojoules per gram. But normally delta U is in kilojoules per mole. So what we have to do is just convert grams to moles. So we need the molar mass of propane 2-ol, which is propanol. So we go and look up the formula for that and we get the molar mass, and then just convert this from grams to moles, and that would give us kilojoules per mole, or would be delta U. Then we have to determine delta H. The way we determine delta H is just like we did for the last problem, and that is we're going to burn propane 2-ol, and this is what it's going to look like here. This is 2-propanol. And then we're going to burn this. So I'm going to make this just a simple molecular formula. It's C3, H2, oh, actually this is 3, 3, 6, 8, O. 2-propanol is a liquid. This is called isopropyl alcohol. This is its common name, or rubbing alcohol. And then we're going to burn it in O2 to form CO2 and water. So let's balance this. We'll need 3 CO2s, 4 H2Os, and that gives us 3 times 2, 6, plus 4 is 10 oxygens. So we'll need 9 plus 1. So we'll need 9 halves here, O2. Then we're going to need delta N of gas. I have 3 moles of gas minus 9 halves moles of gas. And so I'll get it to the same denominator. That's going to give us 6 halves moles of gas minus 9 halves moles of gas, which is going to give us 3 halves, which is minus 1.5 moles of gas. Okay, then we figure out how much work is done. So under normal conditions, this is 298.15, and normal, we're going to do it at 1 atmosphere. So we're going to assume the pressure is 1 atmosphere. And so we have 1.5 moles of gas. At 24.5 liters per mole of gas. $36.75. So the volume is going to shrink by 36.75 liters. The work of the system is equal to minus P delta V. Minus 1 atmosphere times our delta V is minus 36.75 liters. So this gives us plus 36.75 liters atmospheres times 101.3 joules per liter atmosphere. This gives us 3,722 joules of work. And then we're going to convert it to kilojoules, 3.7 kilojoules of work. Since it's a positive sign here, this means the surroundings does the work, the system gains energy. So system gains energy from surroundings. The surroundings did the work because the volume contracted. So delta H is equal to delta U minus the work. So it's going to be equal to delta U minus the work, which is 3.7 kilojoules. But we need the delta U in kilojoules per mole of isopropyl alcohol. And so what we're going to do is we're going to convert it here in part A. We're going to go minus 33.41 kilojoules per gram of isopropyl alcohol. And then I'm just going to get the molar mass of isopropyl alcohol here to save time. Do that. 60.1. So I'll get 33.41 times 60.1, 2007.9 kilojoules per mole, minus 2007.9 kilojoules per mole. Sig figs, I'm allowed 3. So this is going to be equal minus 2007.9 kilojoules per mole minus 3.7 kilojoules per mole. And so this is going to give me minus 2011.6 kilojoules per mole of isopropyl alcohol. And so delta H, we get more heat burning it under constant pressure conditions than under constant volume conditions. And that extra energy and heat came from the surroundings. So those are examples. We have the examples of qualitative and quantitative there. All right, any questions on that? Do you have any questions on other stuff? For the test? Number 45. Which exam? Third exam, number 45. Oh yeah, I forgot. Sorry, I forgot to do this one. Okay, in this one, we're doing calorimetry experiment. And so we're going to do neutralization here. Delta H of the reaction is minus 55.84 kilojoules for the reaction as written. So it's per mole of HCl per mole of sodium hydroxide. And so the first thing is, we know that delta H of the reaction here is minus 55.84 kilojoules. And it's for this reaction here. If 50.0 milliliters of 1.05 molar sodium hydroxide is allowed to react with 25.0 milliliters of 1.86 molar HCl. And so we have HCl and sodium hydroxide reacting. And so the first thing is we have to determine what the limiting reagent is. And so we have 50 times 1.05 moles. And so that's 50 times 1.05 gives us 52.5 millimoles, or 0.0525 moles of HCl. And then we have 25 milliliters of 1.86 molar, oops, that's HCl, this is sodium hydroxide. So let me move this. So we have 0.0525 moles of sodium hydroxide. And then over here we have 25 milliliters of 1.86. So it's 0.025 times 1.86. And that's going to give us 0.0465. So what's the limiting reagent? Hydrochloric acid is the limiting reagent. So we're going to have 0.0465 moles of reaction. So this is the LR. With both solutions at 22.31. And so this is going to be 25 milliliters plus 50 milliliters. And so our product mixture is going to have how many milliliters? 75 milliliters of product solution. Our product solution will be mostly salt water and a little bit of excess sodium hydroxide. plus a tiny bit of excess sodium hydroxide. But we're going to call it product solution. It's just what's left over after the reaction. And that's the product solution. And that product solution is initially at 22.31. What will the final temperature be? And so it's at 22.31 degrees C. This is T initial. And so what they want to know is they want to know what the T mix is going to be. The heat capacity of the container is 10.5 joules per degree C. So Q of the reaction is equal to minus Q of the surroundings. Q of the surroundings is going to equal the Q of the leftover product solution plus Q of the container. The container is our calorimeter in this case. And that's about appropriate heat capacity of the calorimeter. The solution's density is 1.02 grams per milliliter. So the product solution has a density of 1.02 grams per milliliter and a specific heat of 3.98. 3.98. I'll just write it over here. So we break this up into two parts. First, we look at Q of reaction. Q of reaction is equal to the amount times delta H. So the amount of reaction is 0.0465 moles. Yeah, we're out of time, so if you have to leave, it's okay. I'm just going to finish this problem since I started it. Times our delta H, which is minus 55.84 kilojoules. Minus 55.84 kilojoules per mole. Okay, this is going to equal this. So this is going to be minus Q of the leftover. It's an object. So the leftover is equal to the amount of leftover solution times C of the leftover solution times delta T of the leftover solution plus the amount of calorimeter. We only have one container, so it's going to be C of the container times delta T of the container. The container and the solution are in thermal contact, so these two delta T's are the same. And so what we're going to do here is the amount of leftover solution is equal to 75 milliliters times the density of 1.02 grams per milliliter. Okay, that's the amount. And then C of the leftover is 3.98 joules per gram degree C. And delta T, we don't know what that is because we don't know what T final is. Now, the container has a heat capacity of 10.5 joules per degree C times delta T. These two delta T's are the same because they're in thermal contact. And so these two are equal. And so what we do is this. We solve for delta T. Okay, once we get delta T, then solve for T final. T final is equal to delta T minus T initial. Actually, no. T final is equal to delta T plus T initial because delta T is T final minus T initial. So we got to add T initial to both sides. Does that answer the question enough? Okay. Since I'm over time, well, I can stay longer because it's my office hour now, but we can finish this if you want, or you can finish this at home, either. Do you want to finish it now? All right, we'll finish it now. So 0.0465 moles times 55.84. This is going to give us minus 2.5965 kilojoules on this side. And then what I'm going to do is I'm going to multiply this out. So it's going to be 75 times 1.02 times 3.98. 304.47 delta T. The units are going to be milliliters cancel, grams cancel, and that's going to leave me with the joules over degrees C. So this is going to be joules over degrees C plus 10.5 joules per degree C delta T. So I'm going to combine these two terms here. And so 304.47 plus 10.5, that's going to give me 314.97 joules per degree C times delta T. Now this is negative here, so this whole thing is going to be negative. Okay, now I see over here this is negative, so I can get rid of the negative. But I have a problem here because I have kilojoules over here, I have joules over here. So what I'm going to do is I'm going to convert either one to the other. So I'll just convert the kilojoules to joules. So if I convert the kilojoules to joules, I'm going to get 2,596.5 joules is equal to 314.97 joules per degree C times delta T. And then I'm going to solve for delta T. So I'll take this, flip that, times 2596.5. And my delta T is going to be 8.2436 degrees C. Okay, the delta T is equal to T final minus T initial. They give us T initial, so T final. T initial is 22.31 degrees C. Oh, delta T here. Then I'm going to solve for T final. T final will be delta T plus 22.31. So in that case it will be. So T final is going to equal delta T plus T initial. So delta T is here, 8.2436 plus 22.31. 30.55 degrees C will be our final temperature. So 31 degrees, or how many sig figs? They give us 4, so we'll just leave it. 30.553 degrees C. This is an exothermic reaction, so the product mixture should heat up. And so that's what we see. In this case, delta U and delta H are the same. Why? Because there's no gas being consumed or generated. So we started off with 25 and 50, we end up with 75, so there's no delta V at all. So delta U and delta H are the same here. Okay, does that answer the question? All right, if some other questions come up, you can email me. I'll check my email later tonight. Hopefully it goes okay. Thermodynamics is not easy, so, but eventually it'll click.